So unfortunately, I will not talk about the 1-2 system, but I try to focus on this 1-1 system. And I'd like to review our recent activities in this, and I hope I will convince you that the 1-1 system is also interesting. Thank you very much for the invitation. It's a very nice workshop. And so here is my outline, talk. And first, I would like to discuss the electronic phase diagram of this iron selenium sulfur and iron selenium tellurium. And this sulfur substitute system, we found evidence for this very exotic superconducting state, is Bogoliubov surface. We call it alkaline pair state. And in the iron selenium tellurium side, we have evidence that time reversal symmetry breaking, and which actually meets in its topology. Okay? So this work has been done in collaboration with many people because I have been working on this for several years. But the main players of this talk is the Masaki Roppongi, Takuya Nagashima, and Kota Ishihara in my group in the University of Tokyo. And especially I would like to thank the collaboration for MUSR measurements with Tomo Uemura from the University and Ethan Kai from British Columbia. Okay? So let me start with this 1-1 system. I think all of you know this material, and it has a very simple crystal structure because just layers of iron selenium like this. And the most important point of this material is that it has a so-called electron nematic transition at 90 Kelvin, but it doesn't show any magnetic order down to 0 temperature, which is different from 1 to 2. Okay? And so this material is very important material to study the interplay between this nematicity and superconductivity. And you can find superconductivity at 9 Kelvin without any topic. Okay? So we can actually suppress this electrical nematic transition by applying pressure. Okay? But before reaching the so-called nematic quantum critical point, we actually induce the magnetic order in this case. And after having this done, the TC raise like up to 40 Kelvin. Okay? So this is very interesting. So, but we want to try to understand the interplay between the nematicity and superconductivity. Our next strategy is to use the chemical pressure, and so we can actually substitute selenium side with the isovalent sulfur or tellurium. So this phase diagram, we have iron selenium here, and in the left-hand side we have sulfur substitution, on the right-hand side we have tellurium substitution. And in both cases, we can suppress this nematic transition down to 0, like this, without having any additional magnetic order in this phase diagram, up to when you reach this iron tellurium end, in which you have a different phase. Okay? And what is interesting here is that we have actually very large enhancement of the so-called nematic fluctuations, which can be measured from this elastoresistivity measurements. And so in this phase diagram, we found that we have a pure nematic quantum critical point without any magnetism here in sulfur side, and here also in the tellurium side. So in this phase diagram, we have two pure nematic QCPs without having any magnetism. Okay? So then we want to discuss the impact of this nematic QCP in this superconductivity phase diagram. And this TC dependence looks quite interesting. First, you have the first dome, which we call SC1. And outside this nematic QCP in the sulfur side, the TC gets reduced, like 4 Kelvin. And so we call this SC2. Okay? And we have another superconducting dome, which has the highest TC here, which we call SC3. Okay? So it looks like we have 3 different superconducting phases in this single family. Okay, that's already anomalous. Then, if you look at this SC1 dome, it turns out that from the NMR measurements, this dome actually follows the amount of 1 over T1T in this phase diagram, which indicates that you have actually enhanced spin fluctuations, although we don't have any magnetic order in this phase diagram. So you have a kind of remnant spin fluctuations, which is peaked around 10% substitution. So this dome is likely related to the spin fluctuations. So this SC1 may be related to the spin fluctuation. Okay. However, if you go to this side, SC3 side, if you look at the NMR data, 1 over T1T is pretty constant as a function of temperature. So this indicates that there is no significant spin fluctuations in this SC3 dome, at least at low energies, if you believe this NMR measurements. Okay? So it is likely that this SC3 is related to the pure nematic QCT. Okay? So I suggest that this SC3 is coming from the nematic fluctuations rather than spin fluctuations. Okay? Then, actually, what about the superconducting gap structure? So we can actually take a look at the specific heat data. So this is the C over T as a function of temperature for this ion selenium. And you can see that low energy dependency is actually T linear dependence. So this indicates that superconducting gap is strongly anisotropic. Okay? And this is consistent with the STM data showing B shape of the DIDB. And this is also consistent with the quasi-particle interference analysis showing mapping this superconducting gap anisotropy, and it has maybe deep minima or maybe nodes, okay, in this SC1. However, if you go into the SC3 side, you start to see that this flattening behavior in the C over T at low temperatures, indicating that you actually change the gap to a fully gapped state. And actually, you can also take a look at the tunneling data, which shows a U shape, or maybe you can find a flat portion at low bias. Okay? So clearly, this SC1 and SC3 has a different gap structure. This is actually consistent with what I kind of mentioned, that SC1 may be related to the spin fluctuations, and the SC3 may be related to the nematic fluctuations. Okay, and if you go to SC2 side, this was a very surprise because C over T looked completely different. And you can now find a very large residual density of states in the C over T at low temperatures. And if you look at the tunneling data, you actually see that you have a significant zero bias conductance, right? So this is actually consistent with this specific heat. Okay, so the question is, what is this possible SC2? Okay. So let me discuss the superconducting state of this SC2 region. So before that, I just start with a very general kind of classification of the superconducting gap structure. And as you know, you can have a fully gapped state, like in S-wave state, or you can have a point nodes or line nodes. In other words, you have zero-dimensional node or one-dimensional node, right? And you have this kind of three kinds of classes of the superconducting gap. And it has a different low energy quasi-particle density of states, right? And for example, if you have a line node state, and if you actually you will expect that E-linear effects, right, at low energies. But if you just apply a magnetic field, what happens is that you actually create the low energy states immediately, which is called the Borovic effect. So this has been very well known, And this observation can be used as evidence for Leibniz. Okay? So far, so good. However, very recently, there is a theoretical suggestion started by Daniel that you may have another type of superconducting gap, which has actually two-dimensional nodes, or which is called Bogoliubov-Fermi surface. Okay? And this is very exotic superconducting state. And if you have this kind of Fermi surface, you immediately expect that you actually find a zero energy quasi-particle-based state. Okay? But this requires a very exotic superconducting state, which means that you need a time reversal symmetry breaking state. Okay? And this is a seminal work by Daniel. And they actually consider the time reversal symmetry breaking state. And okay, so I don't want to follow this because in front of him. But I just want to mention that broken time reversal symmetry is not a sufficient condition, but it's a requirement. And the actual requirement is that Papian, so-called Papian, should be negative at some certain k. Then these Bogoliubov-Fermi surfaces can be topologically affected. Okay, so that's actually very interesting. But I just asked him, for the experimentalists, how can I understand this? And the quite interesting answer was that it can be understood that you can actually have a spontaneous Borovic effect, even without the magnetic field, because you have a time reversal symmetry. That's the kind of one way to understand this behavior. Okay? Then later on, the group by Taka Shibauchi have kind of considered this possibility in iron selenium-based superconductors. So they actually assumed that time reversal symmetry is broken, right? And then they actually searched certain range of parameters, and they found some parameter range in which you can actually create this Bogoliubov-Fermi surfaces, which is marked by the blue lines. Okay? Then you can immediately calculate the specific heat and the tunneling ratio of states, in which you can easily find these zero energy states and zero bias conductors, which looks like consistent with what we have observed in this FeSe-2 region. Okay? So this is very attractive for experimentalists. However, there is a big assumption that the time reversal symmetry is broken in this material. Okay? So we decided to collaborate with Tomo Uemura to look at the zero field μSR, which is a very sensitive probe of the magnetic field inside the sample. So this can be used as a direct probe of time reversal symmetry breaking. Okay? So we used three different samples, iron selenium here, and two samples in the FeSe-2 region. And in all of these samples, we actually see the enhancement of the zero field μSR relaxation rate below this. Okay? So this is an indication that we have actually static internal magnetic field appearing below TC. This is an indication that the time reversal symmetry is broken in this series. Okay? So this kind of fulfills the requirement of the Bogoliubov-Fermi surface. Okay, so this is a kind of summary of what we have observed. So this is again the pneumatic transition. This is the sulfur formation, and which goes away right here. And superconducting TC jumps from high TC to low TC. And zero bias conductance and residual density of states from specific heat both shows a jump if you get into the FeSe-2 region, right? And this is another measurement from the transverse field μSR that we can actually measure the absolute value of the superfluid density, which is 1 over lambda squared. Lambda is the penetration depth. And this is a measure of the superconducting carrier density divided by effective mass, which is plotted by these red dots. And that quantity can be compared with this normal state carrier density divided by m star, which can be estimated from the quantum oscillation measurements. Because we use the very high quality standard crystals, we can observe the quantum oscillations. And this can be kind of estimated by this dash line. Okay? So as you can see, you have very strong deviations between these two quantities in the SC2 regions, indicating that a significant portion of the carriers remains ungapped. Okay, and this is also consistent with the Vogel Fermi surfaces, because recent calculations of this Vogel Fermi surfaces shows that if you change the degree of time reversal symmetry breaking, you can find a parameter range in which this Vogel Fermi surface can be stable, which is the shaded area. And in this area, the superfluid density should be strongly suppressed from the original value. Okay? And this seems to be consistent with what we observed in our inner data. So from these combinations of these observations, we actually conclude that we have evidence for ultranodal pair state with Vogel surface in this ion cylindrical cycle. Okay? Then I also asked our colleague in ISSP and Professor Okazaki measured the laser alphas in this SC2 region. Okay? And they actually can map the superconducting gap as a function of Fermi surface angle, and they found a strong anisotropy. And there is some extended angle range in which superconducting gap is actually 0, right? So this is also consistent with the presence of Vogel Fermi surfaces. But surprisingly, this SC2 region is outside the nematic QCP, meaning that it's a tetragonal system. And indeed, if you look at the Fermi surface above TC, you actually find a C4 symmetric Fermi surface. But for some reason, this gap anisotropy has a twofold symmetry, right? So we call this nematic Vogel Fermi surfaces. Okay? And the reason why we have this kind of rotational symmetry breaking inside the superconducting state is not really clear. But I would like to mention that there are already 2 theoretical proposals to try to explain this behavior. But I think we need further studies to really understand this behavior. Okay? So far, what we have observed is that the time reversal symmetry breaking is actually throughout this phase diagram. It's both in SC1 and SC2, right? But only in the SC2 region we have evidence for Vogel surfaces. And why SC1 can also break time reversal symmetry is that in this SC1 we have inside the nematic phase, right? So the crystal has already a domain structure, nematic domains, okay? So if you kind of consider the nematic domain boundary, let's say here, you should have D plus S state in the left-hand side, but you have a D minus S state because you have a different geometry of the system, right? And then actually this problem has been already discussed long time ago for the orthorhombic YBCO by Manfred. And I talked to him, and he immediately gets this idea that you could have sign changing order parameter with this e to the I theta prefactor near the domain boundary. And this can induce the time reversal symmetry breaking state inside the nematic phase, right? But in the SC2 phase, which seems to be completely different, but we have evidence for time reversal symmetry breaking, and we have evidence for Fogo-Ribot frame surface. So this is quite unusual, okay? And but this is an open question: why this suppression of nematicity can drive the topological transition? I mean, I would say it's a topological transition to Fogo-Ribot frame surface. So this is, I think, there are many theories here. So I hope somebody can help to understand this behavior. Okay, so far so good. But very recently, there is another kind of theoretical proposals suggested by Andrei Chupko that maybe you don't have Fogo-Ribot frame surfaces, but you have a completely different gap structure due to the nematic quantum critical fluctuations. And he suggested that you actually have a conventional line noise, but there is an extended range that you have a very small superconducting gap like this, okay? And then if you measure specific heat, you can actually have a very large value until you get a very low temperature. So that's what his suggestion, right? But this is actually coming from the strong nematic fluctuations. So he also suggested that this delta is actually distance from the QCP. So if you go away from the QCP, this signature becomes broader, right? So which we can test. Right? And so far we actually have the 4 different samples, and nematic QCP is 0.17, and here is 0.18, up to 0.25, and we basically see very similar kind of things for specific heat and penetration depth, and doesn't show any evidence that this downturn comes at low temperatures. Okay? So I think it is still more consistent with the presence of Fogo-Ribot frame surface. Okay? And there is another kind of evidence from NMR measurements. And here is 1/T1T measurements done by Professor Fujiwara in Kyoto University. And for this purple data, which is in the SC2 region, here is the TC. And usually 1/T1T is getting smaller if you go to low temperature in the superconducting state. However, it's a very surprising result that in this SC2 region we have actually an increase in 1/T1T at low temperatures. So this is quite anomalous behavior. So that indicates that we have some kind of spin fluctuations present even in the superconducting states. But usually if you have a superconducting gap, so frame surface is gone, so you don't have a spin fluctuation. However, so I thought that maybe this enhancement is actually coming from Fogo-Ribot frame surfaces, and if you have a nesting behavior between the Fogo-Ribot frame surface, you may have a spin fluctuation, right? And indeed, very recently, this kind of enhancement can be reproduced by theoretical calculations, considering that you really have the Fogo-Ribot frame surfaces, and you have a nesting behavior, and also so this is actually done by Peter Hirschfeld. Okay? Okay, so let me switch gear to the iron, selenium, tellurium. And another important point of this phase diagram is that presence of the possible topological superconducting, right? And this actually happens if you substitute selenium with tellurium more and more. What happens is that this chalcogen P band is going down from the top towards the Fermi level. Okay, and then electron structure is becoming topologically non-trivial only in this SC3 region, in this total electric phase order. Okay? And then the group by Professor Shin and Hongding have shown that around here you actually see that topological surface states like this. Okay? So they actually suggested that in the bulk you have a superconducting, possibly S-ray, and then you actually can induce the topological superconducting state and the surface state. Okay, so that was a very, very big surprise, right? And more recently, Hanaguri-san, my friend, have shown that there is actually zero bias conductance peak in vortex cores with super high energy resolution. So this is a very good indication that we have a Majorana zero, right? Then, more recently, what happens is that if you go into the superconducting state, this topological state, this Dirac cone, gets gapped. Okay? And so this is an indication that you actually may have a time reversal symmetry breaking. Then you can create this gap. Okay? So I actually extend our zero field VSR measurements to the tellurium side. And then we actually see also that the relaxation rate is going up, actually below TC. Okay? So we believe that we also have time reversal symmetry in iron cell in tellurium. Okay? So I think I have running out of time. So I just want to mention the most key information that previously. They talk about bulk side is a trivial superconducting, okay? But electronic structure is topologically non-trivial. That's why you have a surface state. So then this may be a good candidate for topological superconducting. However, our measurements of NIRSAR detects a deep in the bulk. So this indicates that we actually have the time reversal symmetry breaking superconducting states deep in the bulk. Right? That actually affects the surface states, and you create a Dirac gap. Right? So I can say that here, this is a very rare case that time reversal symmetry breaking meets topology in superconductor. Right? So I think this is quite interesting situation because that, remember, if you go back to the studies of topological insulators, then people actually are crazy about to use the magnetic TIs, right? And then you actually create the Dirac gap in the surface, and then you can have like a hinge chiral currents. Then you can end up with exotic phenomena such as quantum anomalous Hall effect, right? So in a similar situation can happen in superconductors, and you can actually have a topological surface state in superconductors. But here we have a time reversal symmetry breaking superconductivity inside the bulk, and you create the Dirac gap in the surface. So you may have a completely different new kind of situation. So I hope that we have a novel platform for studying the synergy between time reversal symmetry breaking and topological superconductivity in this system. Okay? So I hope I would like to convince you that iron selenium systems are also interesting. So thank you very much for your attention.